Polar navigation. Transport precession is the rotation in degrees of the gyro north with respect to true north. Chart precession is a rotation in degrees for a moving aircraft of the gyro north with respect to the grid north for a given chart. Astronomic precession causes the gyro axis to spin to the right in the northern hemisphere and to the left in the southern hemisphere. Astronomic precession occurs when the aircraft is on the ground or flying. If a pilot has connected the automatic pilot to the gyro compass fitted with a rate correction device, which is properly corrected for astronomical precession, the course followed by the aircraft in still air conditions will be a great circle. In the absence of wind and without the astronomic precession effect, an aircraft would, at a constant gyro heading, follow a great circle line. A polar track, by definition, is a track part of which is included in an area where the horizontal component of the Earth's magnetic field is less than 6 microtesla. There are a few definitions in polar navigation to come to terms with. G is the longitude difference, LM the average latitude, LO the latitude of the tangent. The formulae applied during a transoceanic and polar navigation are: transport precession, transport wander, equals G sine average latitude. Conversion angle is G sine average latitude divided by 2, and astronomic precession, Earth rate, is 15 sine mean latitude. Exercise 1. An aircraft leaves point P, 60 north, 030 west, on a true heading equal to 090, while the gyro compass, which is assumed to be operating perfectly and without an hourly rate corrector unit, indicates 000. The aircraft arrives at point Q, 62 north, 010 west, on a true heading equal to 095. On the journey from P to Q, the gyro compass remains in free gyro mode. If the flight lasted 1 hour 30 minutes, what will be the gyro heading at Q? There's a couple of things going on in this question. There's Earth rate, the movement of the Earth. There's movement of the aircraft, and not just for 1 hour, it's 1 hour and 30 minutes. And also, the initial heading was 090 and the final heading was 095, so there's a 5-degree correction to be applied at the end. Let's have a look at the formulae for this. Earth rate is 15 sine latitude. The mean latitude is between 60 and 62 north, which is 61. So 15 times 61 is minus 13.1. This is multiplied by 1.5 hours for the flight time, giving minus 19.7 degrees. Transport wander, due to movement of the aircraft, is difference in longitude multiplied by the sine of the mean latitude. The aircraft flew from 30 west to 010 west. That's a difference in longitude of 20 degrees, at a mean latitude of 61. 20 degrees times the sine of 61 is minus 17.5. 360, which was the initial indication on the gyro compass. Subtract from this 19.7 and 17.5 to get 323 degrees. And then don't forget, there was a correction between the initial and the final heading of 5 degrees. So add the heading change of 5 degrees to 323 to get 328 degrees. Exercise 2. A pilot is using a polar stereographic chart whose grid is parallel to the zero meridian, with grid north in the direction of the north geographic pole. The grid heading is 045. After switching to mag mode, the compass heading is 220. The INS position at this moment is 76 north, 180 degrees west. The magnetic variation on the chart is 10 east. What is the compass deviation on this heading at this point in time? Let's have a look at a diagram of this. Having drawn a circle with a 0 at the bottom, west on the left, east on the right, we can draw grid north going up the page through the Greenwich meridian. The aircraft is at 180 degrees east-west and is steering 045 grid. This results in a true track measured from the true north pole of 225. Using CDMVT with a variation of 10 east, 225 true becomes 215 magnetic. A deviation of 5 west results in compass of 220. So the compass deviation at this point in time is 5 west. Exercise 3. Consider a diagram where Tn equals true north, Mn equals magnetic north, Gn equals grid north. If the magnetic variation is 65 west and the grid variation, grivation, is 4 east, the correct arrangement of the different poles is shown below. True north drawn straight up the page. Magnetic north is to the west of true north, and grid north is still further to the west of magnetic north. Exercise 4. You plan to fly from point A, 60 north, 010 east, to point B, 60 north, 020 east. The gyro north of the gyro compass, assumed to be operating perfectly with no rate correction device, is aligned with true north at point A. The constant gyro heading to be followed when starting from A, given that the flight time scheduled is 1 hour 30 minutes with a zero wind, is equal to. Let's have a look at the formulae first. First, calculate Earth rate. Earth rate is 15 multiplied by the sine of the latitude. The aircraft was at 60 north, so 15 multiplied by the sine of 60 is 15 times 0.866, which comes out to be 13 degrees. It's in the northern hemisphere, so it takes a minus sign, minus 13. We're flying for an hour and a half, so multiply by 1.5 to get minus 19.5. Now let's look at the transport wander. The formula for transport wander is d long multiplied by sine of the mean latitude. The difference in longitude is 10 degrees, from 10 east to 20 east, at a mean latitude of 60 north. So transport wander is 10 multiplied by the sine of 60. 10 multiplied by 0.866 is 8.66. If you're flying east in the northern hemisphere, this results in a minus sign, minus 8.66. The total wander will be Earth rate plus the transport wander, which is minus 19.5 from before, minus 8.66, totaling minus 28 degrees. The initial gyro heading was 090, so the final gyro heading will be 90 minus the 28 degrees, in other words 062 gyro. The mean constant gyro heading to fly then will be an average of the initial gyro heading 090 and the final gyro heading of 062. This comes out to be 076 gyro. Exercise 5. A polar stereographic chart has a grid printed over it which is parallel to the meridian 054 west. Grid north is in the direction of the North Geographic Pole. An aircraft is following a true course of 330. At position 80 north, 140 east, what is the grid heading? Let's try this with a diagram. Draw a circle and put a west on the left and an east on the right. 00 is at the bottom since we're in the northern hemisphere. Search round for 054 west, which is in the bottom left corner, and draw a line up through the North Pole and label this grid north. The aircraft is at 140 east on the 80 north parallel. It's flying a true course of 330, which you can measure round from the true north in the centre of the page. There's 14 degrees between the angle 040 and 054 west, which can be transferred to where the aircraft is present. By final calculation, we'll end up seeing a grid heading measured from grid north of 136. Exercise 6. On a polar stereographic chart whose grid is parallel with the Greenwich meridian in the direction of the true North Pole, the true orientation of the great circle linking point 62 north and 010 east to a point 66 north, 050 west is 305. What is the grid route at the starting position of this great circle? Using a drawing, draw one circle to represent 62 north, then inside that circle draw another to represent 66 north. Put a west on the left and an east on the right. True north is in the centre of the page. The aircraft is departing from 010 east to the point 050 west. This is a track measured round from true north of 305. Grid north can be transferred through the aircraft position, and a line can be drawn round from grid north depicting a track of 295 grid. Exercise 7. A south polar stereographic projection of the Antarctic regions has a grid printed over it aligned with the 180-degree meridian. The grid course followed by the aircraft is 280 grid. The position of the aircraft is 80 south, 100 east. What is the true course? Making a diagram of this, draw a circle with west on the left and east on the right. The south pole is the centre of the page, and at the top is 000. The aircraft is at 100 east, and this may be drawn round from the 00 at the top. The grid may then be transferred through the aircraft position, and the grid course may be drawn of 280 grid from the grid reference. Measuring round from the true North Pole gives the direction of the aircraft, which is 000 true. Exercise 8. In the polar Antarctic region, a pilot uses a South Pole stereographic chart whose printed over grid is parallel with the 0 meridian, and grid north is in the direction of geographic north along this meridian. The aircraft position is 80 south, 130 east. With its true route 110, what is its grid route at this moment? Drawing a circle to represent 80 south, put a west on the left and an east on the right. The South Pole is in the centre and 000 is at the top. Grid north is aligned up the page, and the aircraft measured round from 000 is at 130 east. Transfer the grid over to the aircraft position and draw a true track of 110 measured round from true north. You can now measure round from grid north and read 240 grid. Exercise 9. At 1840 UTC, a complete failure of the inertial systems of an aircraft flying from London Anchorage occurs over the geographic North Pole. The wind is nil. The grid heading at this moment is 315 grid. The crew then uses the sun to continue the flight. What is the bearing of the sun on occurrence of the failure? The chart used is a polar stereographic chart with the grid parallel to the 0 meridian in the direction of the geographic North Pole. So, draw a circle with north in the centre and west on the left and east on the right, with 000 at the bottom. The aircraft is in the vicinity of the North Pole, and the relative bearing of the sun is minus 35 degrees. The grid heading is 315 grid, measured from grid north, which is drawn straight up the page. The location of the sun at 1840, which is equivalent to 18.7 hours, may be determined by subtracting 12 hours to get 6.7 hours. Multiply this by the Earth rate of 15 degrees per hour to get 100 degrees west. At this position, the bearing of the sun is 325. Exercise 10. On a polar stereographic chart where the Earth convergence between 2 points located on the parallel 60 north is 20 degrees, what is the great circle maximum cross-track difference with the straight line joining the 2 points? There's a formula for this. The vertex, the highest point on the great circle, in nautical miles, equals tan of the convergence angle multiplied by half departure divided by 2. Convergence angle is half of convergence, and convergence was given as 20 degrees. Half of this is 10 degrees.
Departure is not readily apparent, but can be found by deriving d long from the formula for convergency. Convergency equals d long times sine mean lat. 20 degrees from the question equals d long times sine 60. Rearranging, d long equals 20 degrees divided by 0.866, which equals 23 degrees.
Departure by calculation between the 2 points of longitude is 345 nautical miles when it's been multiplied by half. Multiply by the tan of 10 by 345, divide this by 2 to get 30.4 nautical miles. Exercise 11. The control display unit of an INS displays desired track 100, track 120. What is the track error angle? The track error angle is the difference between desired track and track. This is 20 degrees right.